Before that, let me just scan the solutions. Okay. Just give me a minute. I'm just scanning one document. Okay.
Hello, sir.
Yes, please go ahead.
Sir, I had a quick doubt. Sir, I wanted to ask if we get an exam the questions of
Just wait.
transient, semi-infinite, or
Just
the fin.
just wait. Okay, please go ahead.
Sir, I was asking if an exam we get the fin question or the semi-transient, semi-infinite heat transfer or the multidimensional conduction. Sir, how will we find the solutions?
1 minute. Definitely, if the question is there on these topics, this will be doable.
So because we haven't done Fourier series or ERF functions,
That is
error
what I'm
functions.
saying. Even if error function values I have already given in the uh, this presentation, PowerPoint presentation, isn't it? It's already there. So the point I wanted to make here is if something I give on this topic, I don't know. This will be definitely doable based on whatever we have done so far. It's not going to be completely out of box. Okay.
Alright, sir.
Okay. So let us start with the today's class. I think probably this is the last class before the minor examination, isn't it? So let me just start with what we have covered. Okay. So until the last class, what we have covered was uh, we have looked at the concept of boundary layer. Then we have looked at the uh, dimensional analysis. Based on the dimensional analysis, we have said that different uh, dimensionless numbers are going to be important when we are looking at the correlations. Then we have looked at how to calculate uh, the heat transfer coefficient, and after that we have looked at different correlations, isn't it? So again, I have given different correlations here, but as I said in the last class, even though the dimensional analysis gives me the information that what are the different dimensionless groups which are going to be important when we are looking at a particular heat transfer, but apart from that also, most of the time the formulation of this correlation is done in such a way that it is close to reality. Okay, what I mean by that is, if you look at this particular correlation given by Hansen, the Nusselt number is given as 3.66 plus some term is there which is the function of Reynolds number and Prandtl number. So here this value of 3.66 is used. So this 3.66 is not coming arbitrarily. There is some logic behind it. For example, if you solve a laminar flow problem with a constant wall temperature, in that case, for a simple case of laminar flow with a constant wall temperature, if you solve the problem analytically, what you are going to get is Nusselt number comes out to be 3.66. So this particular equation is not completely, based on the data. There is some logic is behind it. Okay, so that is what we are going to look at today. So one simple analytical, derivation we are going to look at for a pipe flow. Of course, this is a very simple case, but even for a simple case of pipe flow, you can see the mathematics becomes, really difficult. That is the point why people have, made the correlation instead of solving it analytically, because that becomes, mathematically almost impossible to solve. Okay. So in this case, consider a tube flow system as shown in the figure. We wish to calculate the heat transfer under fully developed flow conditions when the flow remains laminar. The wall temperature is TW. The radius of the tube is R0. Radius of the tube is R0. And the velocity at the center of the tube is U0. Okay. It is assumed that the pressure is uniform at any cross
Sir,
section. The
yours not
velocity.
visible.
Hello. Yes. Slides are not visible.
Sir, your screen. Yes, sir.
Okay. Let me just share. Is it visible now?
Yes, sir.
Okay. So it is assumed that the pressure is uniform at any cross section. The velocity distribution may be derived by considering the fluid element. Okay. So here this is what the section of the pipe is shown. In this the velocity profile is also shown. In this particular case, clearly for a pipe flow, the along the radial direction, the heat transfer area is going to change, and therefore a shell balance is made. So this is a particular shell with the thickness of delta x along the x direction. So this shell is analyzed separately here. So for this particular shell, if you look at the thickness of the shell is delta x. Again, the the force input on the left hand side is P into pi r square, whereas the force input from the right hand side is P plus dP pi r square. Again, the shear stress is acting in the opposite direction, so that is tau into 2 pi r dx. So this is tau. Okay. So we can make a force balance here for a given shell. So the force balance in this case is going to be the pressure forces are going to be balanced by the shear stress, isn't it? So that is what is being done here. So if you put all the input and output terms here, what you are going to get is pi r squared dp should be equals to shear stress tau into 2 pi r dx. And if you rearrange the term, here, tau can be represented as mu du by dx. So there is minus sign here. I missed the minus sign here. So if you put tau equals to minus mu du by dx, that minus sign get cancelled out. So this right hand side expression is correct. So pi r square dp is given as 2 pi r mu dx du by dr. I just missed the minus sign here. There is a minus sign is required here. Okay, so that probably I will correct it after the class. Okay. So if we rearrange this equation, what we get is du is obtained as 1 by 2 mu r dp by dx into dr. And we can integrate this particular equation. So by integrating this equation, what we get is u, which is nothing but the velocity at any r in the given cross section. So that can be obtained as 1 by 4 mu dp by dx r square per plus constant. Again, we can put the boundary condition. So at r equals to r naught, that means at the surface of the wall, the velocity is going to be 0, and therefore this constant, if you put r equals to r naught here, what you are going to get is this constant value you are going to get in terms of r naught. So that if you put it in this equation, what finally we will get is u is given as 1 upon 4 mu dp by dx r square minus r naught square. So this is the standard equation which we get when we are deriving the velocity profile in Hagen-Poiseuille equation. So that probably you all might have done in your fluid mechanics, isn't it? So I am not going in more detail in this. Okay, so again at the center, when r equals to r naught, the velocity is going to be maximum, that is u naught. So if we put r equals to 0 here, in this case what we get is u naught is obtained as minus 1 by 4 mu dp by dx r naught square. And if you put it in this equation, the velocity distribution in terms of the maximum velocity is obtained as u is given as mu naught in the bracket 1 minus r square divided by r naught square. So this is the standard velocity distribution which we see in the laminar flow. Okay, is it clear to everyone? Hello, am I audible? Hello.
Hello, sir, you're audible.
Okay, so now this is a parabolic distribution which is a characteristic of laminar flow, isn't it? In a laminar flow, you get the parabolic distribution of the velocity, isn't it? So now consider the heat transfer process for such a flow system. To simplify the analysis, we assume there is a constant heat flux at the tube wall. Okay, so now what is this? In order to solve the heat transfer problem, remember, if I go back here now, first we have solved the velocity problem, we have solved the momentum transfer problem, and based on that, whatever the velocity distribution we are going to get it, that we are going to use in the heat balance. That is what the idea is. Okay, again one more simplification, we are assuming that the heat flux at the wall is constant. So this is the wall, this is the wall. At this wall, the heat flux is constant. So Qx is constant. Qx is constant. That means what? dt by dx is going to be constant. Okay. So in this particular problem, there are two cases arise. We are solving only for one case. The case which we are solving here is a constant wall flux. So constant flux at the wall, that is what we are solving. But there is another case that is nothing but a constant temperature of the wall. Remember I said that the Nusselt number comes out to be 3.66 when there is a constant wall temperature. When we are having a constant wall flux, we get another number. Okay, so but we are solving it only for a constant wall flux. Okay. So we assume that there is a constant heat flux at the tube wall. So dQw by dx equals to 0, isn't it? That means Qw is a constant value, and that means what dQw is given as what? Minus k dt by dx, isn't it? So that will be a constant value. Now let us make a heat balance. So what will be the heat input to this shell? The heat input to this shell, and what will be the output to this the shell, and what is the accumulation? Based on that the heat balance is done. So input to the shell is going to be minus k into area, so that becomes 2 pi r dx, dou t by dou r at r, that is the input. Similarly, the heat conducted out from the annular element is going to be dqr at r plus dr. So that is minus k 2 pi r dx, dou t by dou r plus dr, isn't it? So these are the input and the output terms. And there is the accumulation term. This accumulation term is going to be the volume, that is nothing but 2 pi r dr dx, that is the volume, into rho cp u dou t by dou x. So this is going to give me the accumulation term. Okay. So by making a heat balance here, input minus, just wait. Okay, so here the output is output minus input, and that is given as a accumulation here. So what we get is finally here 2 pi r is a constant term, so that get cancel out. K is there, so k will come out. So k goes on the right hand side, so that becomes r rho cpu by k here, and on the left hand side what we are going to get is r dx dou t by dou r, and this term is going to be there at r plus dr, so that becomes dou by dou r. Okay. Okay, so input minus output equals to accumulation is done here, and based on that what we get is dou by dou r in the bracket r dx dou t by dou r, and that is given as r rho cp mu by k. So cp mu rho cp mu by k is given as okay. So r and u, these are taken on the left hand side here, and cp mu rho cp mu, just wait, I think we have missed one term. Okay, okay, it's correct. Okay, so u r, these are taken on the left hand side, so that becomes 1 by u r, and rho cp by k, that becomes 1 by alpha. Alpha is nothing but the thermal diffusivity, so alpha is given as k by rho cp, so that becomes 1 by alpha here. So what we get is the equation number 2, which is nothing but the final heat transfer equation which we have obtained for this system. Now in this particular equation there is a term u. So this u we have taken from the velocity profile which we have obtained earlier. So this is the velocity profile which we have obtained earlier. So we can put it in this equation, and also dou t by dx. Dou t by dx is a constant term, because what we are assuming is a constant wall flux, isn't it? So qw by dx equals to 0. So that means what? Qw is a constant, and Qw is given as minus k dt by dt by dx. So that means dt by dx is a constant. So that is what is put. Dou T by dou X is going to be a constant term. So that we can put it in this equation and rearrange this equation number 2. And what are the boundary conditions here? The boundary conditions are dou T by dou R equals to 0 at R equals to 0. So at the center, dou T by dou R equals to 0 and K dou T by dou R equals to QW equals to constant. This term anyway we are going to incorporate directly here by putting this partial derivative into a normal derivative. Okay, as a constant term. So this is not dependent on the R. Okay. So based on this analysis, now equation number 2 can be rearranged as dou by dou R. UR term are taken on the right hand side. Remember there is a UR term, 1 by UR term. So this UR term is taken on the right hand side. So this equation becomes dou by dou R dou T by dou R 1 by alpha, dou T by dou X mu 0, dou T by dx u0 1 minus R square by R naught square into R. So now this entire thing can be integrated. So by integrating, what we get is R dou T by dou R is obtained as 1 by alpha dou T by dou X. Again, this dou T by dou X term is a constant term. This is a very important factor here. Okay. So if you don't assume that the constant wall flux, in that case your mathematics further become complicated because this dou T by dou X term is not constant. This is also a function of X and R. And in that case, one has to first find out a analytical expression of dou T by dou X in terms of R, and then that has to be put here. So the mathematics is going to be further complicated in case of constant constant wall temperature. But we are doing a simpler case here, that is the constant wall flux. Okay. So again, integrating twice, what we get is T is obtained as 1 by alpha dou T by dou X u naught R square by 4 minus R raised to the power 4 divided by 16 R square plus C1 ln R plus C2. And again, the boundary condition here is dou T by dou R equals to 0 at R equals to 0. So that gives me the first integrating constant C1 comes out to be 0. Okay. Again, the second boundary condition we are already incorporating here by assuming this dou T by dou X as a constant value. So that is anyway taken care. Okay. Now this particular equation of the temperature distribution further can be simplified by assuming that the temperature at the center is, let's say, Tc. Temperature at the center is Tc when R equals to 0. So if we put it in this equation, what we get is T minus Tc. So this C2 comes out to be Tc. So that further simplifies this equation, and what we get is the equation number 3, where we get the temperature distribution as T minus Tc equals to 1 by alpha dou T by dou X mu naught R square by 4 minus R raised to the power 4 divided by 16 R naught square. So this is the final expression which we have obtained for this particular system. So this is the expression which we have obtained by doing the mathematical, substitutions here. Now we wanted to find out the heat transfer coefficient. So heat flux is given as Q is given as HTW minus TB, where TB is the bulk temperature. So bulk temperature again is nothing but the cup mixing temperature or a bulk temperature that can be defined as as we have already discussed that the temperature is going to be the heat transfer coefficient is going to be dependent on not only the variation in density, viscosity, specific heat, velocity and thermal conductivity, isn't it? So here bulk temperature is nothing but the average over all the variable quantities. So you can clearly see the numerator here is 2 pi r dr rho Cp mu T. So these are rho can change as the temperature change is occurring across the radial direction. So if I go back, so temperature here is TW, isn't it? At the wall, the temperature is TW. At the center, the temperature is, let's say, TC. Between TC and TW, there is a variation in the temperature, and because of that, viscosity may change, because of Cp may change, because of the velocity the density may change, and also there is a change in the viscosity change in the velocity taking place. So all these factors are accounted for calculating the average value of the temperature, which is averaged over all the variable quantities. So all the variable quantities are radius is changing, rho is changing, Cp is changing, and velocity is changing, and temperature is also changing, isn't it? So this temperature Tb is nothing but the average temperature over all these variable quantities like R, rho, Cp, and mu. So this is nothing but a bulk temperature, as well as it is also referred as cup mixing temperature. Okay, so now we wanted to find out Tb because the heat flux is given as H in the bracket Tw minus Tb. Tb we can directly obtain from equation number 3. So equation number 3, if we can put it in this particular expression, and integrate it, what we are supposed to get in this case, I have not done that integral directly here, but I am giving you a final answer here. So the bulk temperature is obtained as Tc plus 7 by 96 mu naught u naught r naught square dou t by dou x divided by alpha. So this is what you are going to get from equation number 3 and this definition of bulk temperature. So if you put this equation number 3 in this integral and solve it, what you are expected to get is this next expression, which is given as Tb equals to Tc plus 7 by 96 u naught r naught square by alpha into dou t by dou x. Again, the wall temperature can be obtained directly from equation number 3 by putting R equals to R naught. So by putting that, what we get is Tw is obtained as Tc plus 3 by 96 u naught R naught square by alpha dou t by dou x. That you can directly visualize here. So this is going to become R naught square minus 4. This is going to be R naught raised to the power 4 divided by R naught square. So that becomes R naught square divided by 16. So R naught square you can take it out. So this becomes 1 by 4 minus 1 by 16. So that becomes 3 by 16. Okay. So this you can directly visualize from equation number 3. You can put Tb and Tw in this equation of the heat flux. Again this heat flux can be given as Ka dou T by dou R at R equals to R naught, isn't it? So this is nothing but the heat transfer by the convection should be the heat coming in the system by conduction through the wall. So that is what is obtained here. So this is nothing but the heat coming into the system by conduction at the wall. Again, from equation number 3, we can differentiate this equation number 3 and put R equals to R naught and find out, we can get the gradient, temperature gradient, wall temperature gradient. So that again, by rearranging this both these terms, what we get is the heat transfer coefficient is obtained as, just wait, this area term is not there. Okay, just wait, this small mistake is there. I'll just get rid of this. Just a bit, I will get rid of this. Okay, so there's no area term here. Okay, this area term get cancel out here with both. Sorry for this mistake. Okay, so heat transfer coefficient is obtained as K dou T by dou R at R equals to R naught divided by Tw minus Tb, and we can put all the parameters here. So we know Tw, we know Tb, we have already calculated dou T by dou R by differentiating here this equation number 3 and putting R equals to R naught. So all these terms we know. If we put it in this particular equation, what we get is heat transfer coefficient is obtained as 48 K by 11 D naught. And if we rearrange this, what we get is Nusselt number is given as HD by K, that comes out to be 4.364. So this is very important. Okay. The Nusselt number in a laminar pipe flow with constant wall heat flux is given as 4.364. Directly we can write this. Okay. So that is why you will see that most of the correlations for the constant wall heat flux will start with this number. And in a similar manner, this entire analysis can also be extended for constant wall temperature. But in that case, one more complication comes into the picture, that is this dou T by dou X term. This is not constant. This is not constant. In fact, this is a function of radius r. So this has to be obtained separately, and then this entire analysis has to be done, but that is not been done in this particular case. But if you do that analysis, it is there in several books. What you will get is Nusselt number comes out to be 3.66. So this is the rationale behind using the constants like 3.66 in such correlations. Okay. So is it clear to everyone? Hello?
Yes, sir, it's clear.
Okay. Okay, now let us move to the next topic. See, so far we were looking at the flow through the circular pipe, but in some cases you will see there is a annular flow is there. In some cases you are having a rectangular channel. In all such cases, how to solve the problem? Because most of these correlations are given in terms of the uh, pipe flow, isn't it? Most of the correlations, if you look at, these are for the pipe flow. So can you apply these correlations of the pipe flow for such non-circular geometries? So the idea of using these correlations of the circular systems or a pipe flow for non-circular duct can be done by obtaining the equivalent diameter. So equivalent diameter is nothing but 4 into hydraulic radius. So that is hydraulic radius is given as a cross-sectional area of the flow divided by weighted perimeter. So this we have already seen in the last tutorial class. Uh, if you have seen the last tutorial class, there also we have calculated the um, equivalent diameter for the annular region. So that is obtained as 4 into cross-sectional area of the flow divided by weighted perimeter. So for a rectangular duct of sides L1 and L2, the equivalent diameter can be obtained as 4L1 into L2. So that is L1 into L2 is going to be the cross-sectional area for the flow, and weighted perimeter in this case is going to be 2L1 plus L2. So the equivalent diameter is going to be 2L1 L2 divided by L1 plus L2. That's it. Now, one more important thing to note down. The equivalent diameter for the pressure drop calculation and the equivalent diameter for the heat transfer calculations are not same. This is a very important point to note down. Okay, so let us look at an annular flow. So here you can see from the inner tube there is some fluid is flowing, and from the annular region there is another fluid is flowing. The diameter of the inner pipe is D1 and the diameter of the outer pipe is D2. So in this case, the pressure drop, for the pressure drop calculation, not only this area at this top but also the area at this bottom here in the annular region, both these are important, isn't it, in for the heat transfer calculation. And therefore this weighted perimeter, this weighted word is very important. Weighted in the sense how this particular, whether that particular area is being used or not, isn't it? So the weighted perimeter for the pressure drop calculation comes pi d1 plus pi d2, both this area, the area here surrounding this inner pipe, as well as the surrounding the outer pipe through from the inside. Both these areas are important here. So pi d1 plus pi d2 both are important for the pressure drop calculation, and therefore the equivalent diameter comes out to be d2 minus d1 for the pressure drop calculation. But when we look at the heat transfer calculation, now in heat transfer calculation, this area which is at the top, which is not important for the heat transfer calculation. For the heat transfer calculation, only the area surrounding this inner pipe is important when we are looking at the annular flow, because the heat is getting transferred through this particular wall, and therefore the weighted perimeter in this case is going to be pi d1. That's it. And therefore for heat transfer calculation, the equivalent diameter comes out to be d2 square minus d1 square divided by d1. That's it. So these are the small differences which you have to remember. Hello, is it clear to everyone? Hello.
Yes, that's fine.
Okay. Okay. Now, so far we were only looking at flow through the pipe or flow through the rectangular duct or something like that, isn't it? The heat transfer also takes place whenever there is a external flow. The first case is the flow over a flat plate. So flow across the flat plate. That is the first case. In such cases, the Nusselt number are defined in terms of the distance x. So here x is the distance from the leading edge of the plate. So Nusselt number NUX, which is defined in terms of the distance x from the leading edge, for a laminar boundary layer is given as 0.332. Reynolds number REX raised to the power 1 by 2 and Prandtl number raised to the power 1 by 3. So this particular correlation we have already seen in the last tutorial. Again, this particular correlation is valid when Prandtl number is between 0.5 and 50. And the Reynolds number, again, this Reynolds number is calculated based on the distance x from the leading edge. So that should be less than 5 into 10 raised to the power 5. So this 5 into 10 raised to the power 5 is a critical Reynolds number for the flow over a flat plate. So when Reynolds number is less than 5 into 10 raised to the power 5 for the flat plate, flow over the flat plate, then the flow is laminar. Okay. Beyond this, there is a transition zone. Beyond this, there is a transition zone. Okay. Again, for a turbulent zone or a transition zone, the Nusselt number is defined as 0.0296 Reynolds number raised to the power 4 by 5 into Prandtl number raised to the power 1 by 3. And this particular equation is valid for Prandtl number between 0.6 and 60 and Reynolds number between 5 into 10 raised to the power 5 and 10 raised to the power 7. So this is valid not only for the turbulent zone, but it is also valid for the transition zone. So remember, transition zone starts from 5 into 10 raised to the power 5 to 10 raised to the power 6, isn't it? So between this limit, there is a transition zone, and beyond that, there is a turbulent zone. So these two equations we have anyway used in the tutorial, so I'm not going in detail of this. Again, similar to flow over a flat plate, we can have a flow past cylinder. So in such cases, the correlation is given by a fan. So Nusselt number in this case is defined in terms of the diameter of the cylinder. So that is why the Nusselt number is defined here as NUD, which is given as HD by K. Again, that is given as 0.35 plus 0.56 Reynolds number raised to the power 0.52, and this entire thing is multiplied by Prandtl number raised to the power 0.3. Here in all these correlations you can see the Nusselt number is related to Reynolds number and Prandtl number. So for all such cases, if you apply a dimensional analysis for a flow over a flat plate or a flow over a cylinder or a flow past sphere, in all such cases, if you apply a dimensional analysis, what you will see that the Nusselt number, Prandtl number and Reynolds number are related. How these are related, that is not clear. How these are related, that is not clear. Remember, that is what we have concluded in the dimensional analysis part. There we have said that the Buckingham pi theorem only gives that these are the Reynolds number, these are the dimensionless number which are going to be related with each other, isn't it? But how these are related, that exact relationship is not known based on the pi theorem, isn't it? Okay. Again, for the flow past sphere, we can get Nusselt number is given as HD by K, and that is given as 2 plus again 0.4 Reynolds number raised to the power 1 by 2 plus 0.06 Reynolds number raised to the power 2 by 3 into Prandtl number raised to the power 0.4 in the bracket mu by mu W raised to the power 2.25. This particular correlation is given by Whittaker. Is valid in the range when Reynolds number is between 40 and 105, Prandtl number is between 0.65 and 300, mu by mu W is between 0.25 and 5.2. Again, one more thing to note down here is, remember here Nusselt number is given as 2 plus something. So the important point to note down is if we solve the flow path sphere problem for a laminar Stokes flow, analytically you can prove that Nusselt number comes out to be 2. This we can analytically we can prove. In fact, this is one of the unsolved problem given in the book. Okay. So Nusselt number is obtained as equals to 2 when we are looking at the laminar Stokes flow. In fact, this was one of the problem I have given in the exams earlier. Anyway. Okay. So the point I wanted to say here is there are many correlations are there in the book. I have only given few correlations in the slide. Because you can look at all these correlations from the book directly. There is no point in discussing these correlations because these are anyway available to all of you. The students are advised to refer the book for other correlations. So please do not rely only on these correlations which I have given in the slide. This I am requesting all the students. You all have to go through the other correlations which are there in the book. I have given only the selected ones. I have not given all the correlations here. All right. Hello.
All right, sir.
Yes, sir.
Okay. Okay. Now let's move to another system. This is a very important system. This is very important because this is so regularly used in the industry. Okay. So flow across the bank of the tubes. So here the example given is a waste recovery from the flue gases by the water flowing through the tubes. So these are the different tubes are there, isn't it? So these tubes are moving in the direction of the plane. So here you can see these are the cross section of the tube. So these are moving as the screen is there, isn't it? In the Z direction these are moving. Okay, so the length is in the Z direction for these tubes, and the cross section is shown here, and the flue gases are moving in a X direction. The flue gases are moving in a X direction. So I am probably I can show you X and Y direction here, so you will be able to visualize what I'm trying to say. Okay. So this is the X direction. This is the Y direction. X direction is so this is X direction. And this is Y direction. So tubes are arranged. Tubes are arranged in a Z direction. So Z direction is perpendicular to the plane. Z direction is perpendicular to the plane. Okay. And the flue gas is flowing across these tubes in a X direction. So the flue gas is flowing across the tubes along the X direction. Okay. Now what is happening here is, so the temperature of the flue gas on the left hand side is, let's say, T1, and the temperature on the right hand side is T2. So temperature here on the left hand side is T1, temperature on the right hand side is T2, isn't it? So as the flue gas move across this bank of the tubes, the heat is getting transferred because the water is flowing through this tube. So this water flowing through this tube takes the heat from the flue gas, and because of that this flue gas cools down as it moves along the X direction. Okay. Again, this is commonly used, heat exchanger for recovering the heat from the flue gas. Again, there are two configuration in which the tubes are arranged. So the first configuration is the aligned one, where the tubes are arranged in a properly aligned manner, whereas there is another configuration in which the tubes are arranged in a staggered manner. Okay, so in a aligned tube, there are two parameters. One is the SL, which is nothing but the longitudinal pitch, which is nothing but this particular distance. So distance between two tubes in a x direction is nothing but the longitudinal pitch, whereas the distance between the two tubes in the y direction is nothing but the transverse pitch. So in addition to longitudinal pitch and the transverse pitch, there is a diagonal pitch is present in case of a staggered arrangement. So in the staggered arrangement, the distance between these two tubes is nothing but the diagonal pitch. Okay. Now the correlations are given for such systems. So the commonly used correlation for such system is Nusselt number, which is defined in terms of the diameter of the tube. So this diameter of the tube is D. Maybe I'll just put it D here. So in order to avoid the confusion. So diameter is D. So this Nusselt number is defined in terms of the diameter of the tube. Diameter of the tube. This is a very important thing here. That is given as HD by K, which is given as C into Reynolds number max raised to the power m into Prandtl number raised to the power 0.36, and again in the bracket Prandtl number divided by Prandtl number at wall raised to the power 0.25. So this basically gives me mu by mu w. That's it. Prandtl number is Cp mu by K. So Cp is constant, K is constant, and Prandtl number at the wall is going to be Cp mu wall at Cp mu w by K. So this is going to give me mu by mu w directly. Okay. Again here the Reynolds number is based on the diameter of the tube and maximum velocity, and therefore it is defined as RD max, RED max. So this RED max is nothing but the Reynolds number defined in terms of diameter of the tube and maximum velocity. So this is given as d rho V max by mu. So V max, which is nothing but the maximum velocity. Why we are saying the maximum velocity? Because as the flue gas, which is having a velocity of V, moves across this bank of the tube, here the cross sectional area is going to reduce because some of the area will be occupied by the tube. And since the area is minimized, the velocity of the fluid flowing across this tube is going to increase, and that velocity is defined as maximum velocity. So the maximum velocity Vmax in this case will be given as St by St minus D into V, where V is nothing but the upstream velocity for the aligned arrangement. And similarly for the staggered arrangement, Vmax is defined as St divided by 2 Sd minus D into V, where Sd is nothing but the diagonal pitch. So we are going to solve one problem based on this in the next tutorial. Again, one more important point to note down here is, as I said, the temperature on the left hand side is, let's say, T1, and temperature on the right hand side, let's say T2. As the flue gas move across the bank of the tube, the temperature is going to drop. But the temperature of the fluid which is flowing through this tube, remember the boiler water is flowing through each of these tubes. So temperature of that water is fixed, and therefore the wall temperature of each of these tube is fixed. So clearly the temperature difference at one end here is going to be what? TW minus T1, whereas the temperature difference on the right hand side is going to be what? TW minus T2. And this TW minus T1 and TW minus T2, this temperature difference is going to be different as we move from left hand side to right hand side. And in such cases, therefore, what we have to use is log mean temperature difference. Remember, that is what we said, when the driving force is changing as we are moving along the x direction or along the length. In such cases, instead of using the normal temperature difference, what one has to use is log mean temperature difference. And therefore in this case the temperature which has to be used is log mean temperature difference, which will be defined here as Ti minus Ts. Ts is nothing but the wall temperature, and minus T naught minus Ts. So T naught is nothing but the temperature at the left hand side. Sorry, T naught is going to be the temperature on the right hand side. Ti is going to be the temperature on the left hand side, and delta Tm is going to be the log mean temperature difference. Again, as I said, there are different configurations are there: aligned, staggered, and also the Reynolds number is going to vary. So depending on that, there are different configurations are possible. One is aligned and the Reynolds number between 10 raised to power 3 and 2 into 10 raised to the power 5. Another is aligned, but the Reynolds number is above this particular limit. Then there is a staggered arrangement when in which ST, which is nothing but the transverse pitch divided by SL, which is nothing but the longitudinal pitch. If it is less than 2 and the Reynolds number between 10 raised to power 3 and 2 into 10 raised to power 5, in that case different constants of C and M has to be used. So these are the different configuration. For different configuration, the constant C in this equation and the constant M has to be selected from this table, and then based on that the correlations has to be used to calculate the heat transfer coefficient. So anyway, we are going to see this particular case in more detail when we look at the tutorial problem. So in the next tutorial, we are going to look at the problem solved on this. Okay. So like the flow past the bank of the tube, in most of the chemical applications, you will see there is a packed bed or the fluidized bed where the flow is taking place across the different packings. These packings could be in a spherical shape, or this could be in some other shapes also. So in such cases, for a packed bed, the heat transfer correlation that has to be used is given here. Here epsilon is nothing but the voidage factor. ST is the Stanton number, which is nothing but Nusselt number divided by Prandtl number into Reynolds number into Prandtl number raised to the power 2 by 3, and that is given as 2.06. Reynolds number raised to the power 0.575. Here Reynolds number is defined in terms of the diameter of the particle, and therefore this is given as I between 0.7, Prandtl number equals to 0.7, and Reynolds number between 90 and 4000. Again here Reynolds number is defined in terms of superficial velocity and diameter of the particle. A similar correlation is there for a fluidized bed. So this is a Nusselt number given as NUDP is given as HDP by K, 2 plus 0.6 Reynolds number raised to the power 1 by 2, and Prandtl number raised to the power 1 by 3. So there are few more correlations are there in the book. I have not put it here. So the idea is I have given only selected correlations, but for detail, I advise all the students to go through other correlations which are there in the book. Okay. Clear?
Yes, sir.
Again, here you can see this particular equation is valid only when the flow, if I Nusselt number is given as 2, so this 2 always comes when there is a flow across the sphere. Okay. Okay. Important factor now. Important. So we wanted to see the heat transfer with a variable driving force. Remember, so far whenever we have seen that if the driving force delta T changing across the length, we have used delta T LMTD, log mean temperature difference. At that time I said that we are going to see the derivation of that later, isn't it? But for a time being, let's assume that whenever there is a temperature difference or a temperature driving force is changing across the length, in such cases we have to use a log mean temperature. So let's derive that. Okay. So the calculation of the rate of heat transfer becomes very simple if the overall heat transfer coefficient, the area of the heat transfer, and the temperature driving force all remain constant, isn't it? So when the transfer coefficient is constant, area of the heat transfer is constant, and the temperature driving force is constant. Okay, but if you look at most of the practical cases, more than one of these are varying. So if you are looking at the cylindrical system, then the heat transfer area is varying. Again, when we are looking at the boundary layer heat transfer, there the heat transfer coefficient is varying as we are moving from x equals to 0 to some value x equals to L. So as we are moving from the leading edge, the heat transfer coefficient varies. Correct. So in a similar manner, there is an important case when the driving force itself is varying as we are moving along the length, and that is seen in most of the heat transfer equipments like the double pipe heat exchanger. So this is a double pipe heat exchanger. Here you can see This is a double pipe heat exchanger with a co-current flow. So the end one of the double pipe heat exchanger in which the hot fluid is coming in. The flow rate of the mass flow rate of the hot fluid is mh. The temperature of the hot fluid is th1, and the outlet of the hot fluid is the mass flow rate is mh and the temperature is th2. Again, the cold fluid is flowing through the annular region outside this inner outside of this inner tube in a annular region. So the inlet is MC TC1. So this is nothing but the mass flow rate of the cold fluid, and this is the outlet of the mass flow rate of the cold fluid, which is MC, and the temperature is TC2. So here what we have to note down is, as we move along the length from the location 1 to location 2, here the temperature difference is what? At location 1, at this end left hand side, the temperature difference is Th1 minus Tc1. Whereas when we are looking at the another end 2, here the temperature difference is Tc2 minus, sorry, Th2 minus Tc2, and both these temperature differences are different. And as we are moving along the length of this heat exchanger from left to right, from 1 to 2, my temperature difference is changing. It is not constant. My temperature difference is changing. Okay. So now let us see in such cases what temperature difference one has to use for the heat transfer calculation, isn't it? So this is the typical temperature profiles for the double pipe heat exchanger in a co-current flow. This is the co-current flow. Here, why we are saying co-current flow? Because the direction of the hot fluid and direction of the cold fluid both is same. So here hot fluid is also moving from location 1 to 2. Similarly, the cold fluid is also moving from location 1 to 2. Both the directions are same. Both the directions are same. So here the temperature profiles are obtained as shown in the second figure. Here you can see the temperature Th1 is getting dropped from Th1 to Th2, which is shown by a red line. And similarly, the temperature of the cold fluid is increasing from Tc1 to Tc2. The temperature difference at the location 1 is delta T1, which is nothing but Th1 minus Tc1. And temperature difference at the location 2 is Th2 minus Tc2. And at any location in between, here at any location at the distance x from the left hand side, the temperature difference is delta T. And clearly here in this case, the temperature difference is varying along the length, even though the area, cross-sectional area is remaining constant, heat transfer coefficient is constant, still we have to make a shell balance. And that is why a shell of area dA is assumed here in between. So can you see the rationale behind using the shell balance here? Since here in this case the heat transfer coefficient is constant, here the cross-sectional area is also constant, but the temperature difference delta T is not constant. It is varying as we are moving from left hand side to right hand side from 1 to 2, and therefore a shell is assumed at any distance x from the left hand side with the area of dA. So the temperature at this shell, the temperature of the cold fluid is Tc, and similarly the temperature of the hot fluid is Th. So the temperature difference at this shell is delta T. Okay. Another point to note down in the co-current flow, when both hot fluid and cold fluid are moving in a same direction, in such cases, the outlet temperature of the cold fluid, will never be, above the outlet temperature of the hot fluid. So Tc2 will always less than Th2. It is not going to cross this particular temperature. This is very important. This is a very important factor, because that gives rise to another contacting pattern, which is called as a counter current flow. Okay, so now let us look at the counter current flow also. Anyway, we will do the analysis only for the co-current flow, but for sake of appreciating why counter current flow is important, let's look at the counter current flow here. Now, unlike the previous case, here the direction of the hot fluid and the cold fluid is opposite to each other. So the hot fluid is flowing from location 2 to location 1, whereas the cold fluid is flowing from location 1 to 2. So the direction of both these fluids is opposite. Now in this case you can see in this case you can see the temperature difference at the end 1 is Th1 minus Tc1, and similarly the temperature difference at the location 2 is Th2 minus Tc2. But the point to note down here is the temperature Tc2, which is the outlet temperature of the cold fluid, which can be above the temperature Th1, which can be above the temperature outlet temperature of the hot fluid. But in this case you can see that outlet temperature of the cold fluid can never be above the outlet temperature of the hot fluid. But in case of the counter current flow, the outlet temperature of the cold fluid can be above the outlet temperature of the hot fluid. So in some cases where the outlet temperature of the cold fluid is given above the outlet temperature of the hot fluid, that's a clear indication that the contacting pattern is a counter current flow. Even though it is not mentioned in the problem or not mentioned in the system, it's a clear indication that it's a counter current flow. Is it clear to everyone? Hello? Is it clear to everyone what we are saying? What I'm saying is, if the outlet temperature of the cold fluid is above the outlet temperature of the hot fluid, remember here Th1 is the outlet temperature of the hot fluid. In that case, it's a clear indication that it's a counter current flow. It's a counter current flow if it is not mentioned in the problem. And again, this can be, this I'm saying can, this can be above Th1. It may not be sometimes, isn't it? But the outlet temperature of Tc2, the possibility of having a higher value of Tc2 above Th1 is exists only in the counter current flow. Only in the counter current. Okay. Now let us analyze this co-current flow in more detail. Counter current flow we will not analyze, that you can do yourself. You are going to get the same answer, but we will analyze this co-current flow in more detail. So we have taken a shell at any location X from the leading edge, from the left hand side here, with a area of dA, and let us find out what will be the temperature difference one need to look at whenever there is a change in the driving force delta T1, change in the driving force delta T as we move across the length of the heat exchanger. Okay. So applying the heat balance over a small area dA of co-current flow case. So dQ is nothing but the rate of heat transfer in the shell, which can be given as UdA. dA is the area of the shell which we have assumed, element we have assumed, and temperature difference is going to be Th minus Tc. That is what we have seen. The temperature is going to be Th minus Tc, area is going to be dA, and the heat transfer will be dQ. So dQ is given as UdA Th minus Tc, and that can be given as UdA delta T, where delta T is nothing but Th minus Tc. Also at the shell, what we can say that the heat lost by the hot fluid should be same as heat gained by the cold fluid, and therefore dQ can be given as minus mh Cph dTh should be same as mc Cpc dTc. Now here the negative sign is used because as we move along the x direction here, the temperature of the hot fluid is decreasing, and therefore the minus sign is there. Therefore the minus sign is coming here. Okay. Now from equation number 1, we can clearly write down the expression for Tc. So Tc can be given as delta, we can write down the expression for Th. So Th can be given as delta T plus Tc, and that we can put it in this particular equation, in this equation number 2. So dQ is given as minus mh Cph d, dQ is given as minus mh Cph d, and delta, this Th is replaced by delta T plus Tc, in this equation. So this becomes d in the bracket delta T plus Tc equals to mc Cpc dTc. Again, this bracket can be differentiated because the derivative sign is there outside. So this we can differentiate. So by differentiating, what we get is d delta T minus ms Cph dTc dTc, and that should be equals to, again we can rearrange these terms little bit. So mHCpH d delta t as it is minus mHCpH this first term as it is, and dTc from this equation number 2, dTc can be given as dq divided by mccpc. So dq divided by mccpc will be dTc, so that we can put it in terms of this dTc. So what we get is minus mHCpH d delta t minus mHCpH in the bracket dq by mccpc. Now this dq term is there on the right hand side, there is a dq term on the left hand side. We can collect both this dq term on the left hand side. So this becomes dq in the bracket 1 plus mHCpH divided by mccpc, because this becomes mHCpH divided by mccpc minus sign. We take it on the left hand side, that becomes plus. So dq 1 plus mHCpH divided by mccpc is equals to this factor remaining, which is nothing but minus mHCpH d delta t. If we rearrange this, what we get is dq is given as again minus mHCpH mccpc divided by mHCpH plus mccpc d delta t. So this bracket is simplified here. So this becomes mccpc plus mHCpH divided by mccpc, and if you take this mccpc on the right hand side, there is a mHCpH, so that becomes mHCpH into mccpc, and this mccpc plus mHCpH on the left hand side comes in the denominator here. So this is equation number 3. Now again from equation number 1, dq is given as u dA delta t. We can put this u dA delta t in this equation number 3. So what we get is u dA delta t, and this right hand side remain as it is as minus mHCpH mccpc divided by mHCpH plus mccpc into d delta t. Now there is a d delta t term is there, derivative of delta t, and there is a delta t term is there on the left hand side. So this delta t term we can move it on the right hand side, and this entire factor we can move it on the left hand side. So what we get is d delta t divided by delta t equals to minus mHCpH plus mccpc divided by mHCpH mccpc into uda. So we have got a equation in terms of differentials here in equation number 4. So this equation number 4 is we have obtained. Now in this equation number 4, again this negative sign we can take it on the left hand side, and we can integrate it between delta t1 and delta t2. So at location 1, the temperature difference is delta T1, which is nothing but TH1 minus TC1. At location 2, the temperature difference is delta T2, and the area at the location 1 is going to be 0, and the area at the location 2 is going to be this entire area. So that becomes area equals to A, and therefore in this case the boundary conditions are at 1 A is 0, delta T is delta T1, and at 2 A is A and delta T is equals to delta T2. So we can integrate this equation, and by integrating this equation what we have obtained is ln delta T1 by delta T2 is equals to mHCpH plus mccpc divided by mHCpH into mccpc into UA, where U is the overall heat transfer coefficient and A is the area. So this is the equation number 5, which we have obtained by integrating this equation number 4 between the given limits delta T1 and delta T2. Now in this case, this factor mHCpH plus mHCpH divided by mHCpH mccpc, this can be omitted by making a overall balance. So let us make a overall balance between these two ends. So between these two ends, whatever the heat lost by the hot fluid should be same as whatever the heat gained by the cold fluid, and that is what is written here. So heat lost and heat gained both should be same, equals to Q, and that is given as heat lost is given as mHCpH TH1 minus TC2. So this is the balance between both the ends 1 and 2. So the temperature is changing between end 1 and 2 is TH1 and TH2. Therefore, the entire temperature difference is TH1 minus TH2. And that should be same as heat gained by the cold fluid over the entire length L between the location 1 and 2. So that is given as mccpc TC2 minus TC1. Now from this equation, Q by MHCPH is given as TH1 minus TH2. Similarly, Q by MCCPC is given as TC2 minus TC2, and both these factors can be summed up. So Q by MHCPH plus Q by MCCPC, that is given as TH1 minus TH2 plus TC2 minus TC1, and this right hand side can be rearranged. So TH1 minus TC1 we can put it as a one factor. So what are the remaining thing? Remaining thing is minus TH1. So we can take a minus sign here, and another bracket we can have TH2 minus TC2. And remember, TH1 minus TC1 is nothing but delta T1, whereas TH2 minus TC2 is nothing but delta T2. So that means delta T1 minus delta T2 is nothing but this entire factor which is there on the left hand side. So this left hand side factor can be rearranged as Q. We can take it as a common, and what we can have is MHCPH plus MCCPC divided by MHCPH MCCPC. So this is the same factor which we are having in equation number 5. So this factor in the equation number 5 can be replaced by delta T1 minus delta T2 divided by Q. So if we replace that from equation number 5 and equation number 6, what we get is Q is obtained as UA delta T1 minus delta T2 divided by ln delta T1 by delta T2. So this is nothing but UA delta T LMTD. So now is it clear to everyone why we are getting a log mean temperature difference here? Hello? Hello? Is it clear to everyone? Am I audible? Hello?
Yes,
All
sir.
are
Yes,
lost?
sir, you are. No, sir.
Okay. Sometimes, teaching on this MS Teams becomes monotonous because it seems like I am teaching to the screen. I am not able to see whether the students are appreciating or not, whether they are getting it or not, whether my pace is too fast, or whether I need to slow down a little bit. All these inputs I get it when I do the class in the actual class. But in online thing, that type of input is not there, isn't it? So it becomes monotonous sometimes. Okay. Anyway, so the point which I wanted to make it here is, for a co-current flow, the heat transfer Q is given as UA delta T LMTD and not UA delta T. Why? Because the temperature difference delta T is varying as we are moving from location 1 to 2. Now the another question you can ask, if let's say delta T1 is same as delta T2, in that case the Q is obtained as UA delta T1 or delta T2, doesn't matter. Okay, you can directly get it from this equation. If you apply a Hospital's rule, then what you are going to get is Q is obtained as UA delta T. That's it. Again, the same expression you are supposed to get if you solve. Remember, in this case, we have solved it for co-current flow. But if you do the same analysis for this counter current flow, which is the second figure, then you are going to get the same thing. In fact, this derivation is given in the book. You can just go through the derivation given in the book. So for a counter current flow also you will get the same expression you are expected to get. I have done the derivation only for the counter current flow. For a only for the co-current flow. For a counter current flow, you are supposed to get the same expression. In case of counter current flow, also Q is given as UA delta T LMTD. That's it. So there's a last topic, but I think it is too much for today. So I will not cover this last topic. We will cover this part maybe in the next class. But I wanted to discuss about the quiz little bit, and then we will stop. Is it all right? Hello? Is it all right?
Yes, sir. We still have some time before the
Okay.
next class.
So I will just quickly share you the solution of the quiz. Anyway, most of the students have done well. In fact, there are 4 students who got out of marks. Unlike the last year when there was lot of chaos in conducting the examination, but this time I felt the quiz one was very smooth. Uh, Not only for me but also for you, because I got less queries and I could see that many students have done well. Uh, there is a request from one student, I don't remember the name. the request was to change the examination from the normal answer numerical type answer type of quiz to the essay type of quiz, where you will upload your answers and then I have to grade all your answers on a Moodle. But that is not realistic. I'm really sorry to say, but that is not realistic in the sense, because I do that. I generally do that for a size of 50 students when I used to teach the elective course. So in every next semester I'm going to take the elective course. I have done the elective course in the last semester. So in all the elective courses I do that type of grading, because I can give you the marks on your steps also there. But that thing is not feasible in this case, because the number of students here are around 200. So checking 200 copies on a computer online is not feasible. It's really difficult. I can check 500 copies offline. There's no problem. But checking 200 copies directly on the screen is really difficult, because I have to mark each and every copies using some digital pen. It's really painful. So that option is uh, not feasible, is not possible in this case, because the number of students are 200. And I don't want it to give the grading to the TS. It's not good. So mostly the quiz and other things, mostly I wanted to grade it directly. So whatever we are doing, that is the most feasible one. And this time students have done well. So I am confident that you are doing well in a way. So except one or two students, but probably they will also improve in next time, because it's constantly evolving system, isn't it? So you will also evolve with time. Whatever mistakes you are doing this time, probably you will not be doing those mistakes next time, isn't it? So we will continue with the same type of examination. Is it all right? Hello, is it all right?
Yes, sir, it is fine.
Okay. Another thing is one more thing which I wanted to tell. Monday batch tutorial. Monday batch tutorial, whatever we have done in the tutorial class, there is some mistake. There is some mistake in my answers which I have given, because we were extending after 1 hour. So I have given the last part in a little bit in a hurriedly manner. What I am asking all Monday batch student is, there is a recording of the Tuesday batch student. A more correct solution is given in a Tuesday batch tutorial. Okay, so please go through that video. Don't go through the Monday batch video. Please go through the Tuesday batch video of tutorial. I have uploaded the correct version of the whiteboard screen on the MS Team. But for video, please go through the Tuesday batch tutorial. Okay, that is the request to all the Monday batch students. Okay. So let me share the solution. So is it visible? The solution is visible to everyone?
Yes, sir.
Okay. So first problem was very easy. Mostly half of the part we have already solved in the class itself, isn't it? Only you have to put the values and get the answer. So from the heat balance, what equation we are expected to get is this equation. Then you can integrate this equation twice. What we are going to get, minus IV by 2k x square plus C1 x plus C2. This psi v, I have used the value of 80 into 10 raised to power 6, but this psi v value was different for different student. This k value was different for different student, and also this x value was different for different student. And based on that, you can apply the boundary condition. So at x equals to 0, the temperature was 160, and at x equals to whatever the value was there for your case, the temperature was 120. You can put it in this equation and obtain C1, C2. And then you get the temperature distribution equation. You can differentiate this temperature distribution equation and equate to 0. You will get the location for the maximum. location for the maximum. I could see maximum, almost 95% students have done both these parts correctly. Part A and part B. This almost 95% students have done well. Some students have made mistakes. In part C, what you have been asked to calculate was what will be the heat flux at this location, what will be the heat flux on the right hand side, and what will be the heat flux at the center. That is what the question was. So again, the heat flux on the left hand side comes out to be negative. That comes out to be this C1 into K, this C1 into K minus K. Some students have missed the minus sign or something, but these are the places where the students have made some mistakes. So mostly the problem number one, almost everyone have got the correct answer. So almost if I look at almost 90% students have got this first question correctly. So okay. Second question was a little bit difficult, but not difficult because similar problem we have solved earlier. So how to calculate this Q, that part was very clear because one example we have solved similar to this. So I square rho is going to give me Q. Here also this radius was varying. Also this current I was varying, and the transfer coefficient H was varying. Okay, so the first thing was very clear. You have to calculate Q as I square rho, and that you can directly obtain based on the values given. So this part mostly people have done correctly. Then we wanted to find out what will be the surface temperature in the steady state when we are giving a infinite amount of time. Then what will be the steady state temperature, that we can just find out by making a steady state balance. So whatever the heat generated, that should be same as the heat taken by the convection. So that becomes HA Ts minus Ta, where Ta is the ambient temperature. So that is already given. So Ts we can back calculate. So this people have done it correctly. Then part C, D, E, these were on the unsteady state. So if you make a unsteady state balance, in this case I have done the unsteady state balance. So the accumulation terms is given as mcp dt by dt, generation minus whatever the heat is taken out by convection. So that becomes HAT minus Ti. So if you integrate it in terms of the dimensionless temperature, what you get is this equation. T bar is given as Qg, which is nothing but the heat generated, divided by Ha, 1 minus exponential minus Ha by mcp T. So this you can represent in the form of C 1 minus e raised to the power minus d by T minus d dt, bracket close. So here the question was asked to calculate the value of C and calculate the value of D. I have given even this form of the equation. I have given the form of this equation also because I don't wanted you to derive some other form, and then it would have been difficult to grade. So I have even given the form where you have to find out C and D. So C is obtained as Qg by Ha. So that comes around 17.51 in my case for the given values, and D is Ha by mcp. Again, all these values were given, so you can calculate D. The last part was how much time will be required to attain 63.2% of the steady state temperature rise. So the new temperature rise is going to be the steady state value Ts minus Ti multiplied by 0.632. So this value we already know. So from that we can find out T minus Ti, which comes around 11.0.66 in my case. That you can put it directly in this equation. In this equation C and D, you back calculate the value of T. So value of T in this case comes around 121.59 second. Okay, so this was also easy. So only message I wanted to give all the students who messed it up this time is, doesn't matter. You try to do well in your minor, you try to do well in your quiz too, because anyway we are going to count based off 2 quizzes. So if you do best in this quiz, it's okay. If you don't do best in this particular quiz, there is one more chance to do the best, isn't it? So in the next quiz you do well, and that will be counted. That will be counted. Okay, but please try to do things carefully. Generally the questions are not lengthy. Sufficient time is given. You have all the time available with you. Don't make silly mistakes, because anyway it is corrected mostly by the Moodle. I only cross check if there is a query, but uh, you know only the legitimate queries are answered. If you send some unrealistic queries, this will not be answered. Okay, so the syllabus for the minor one is whatever we have covered till today. I am going to update the corrected version of this PowerPoint presentation on Moodle. And best of luck to everyone. Can we stop here unless you have any question? Hello.
Thank you, sir.
So when we are having the minor one, date, anybody can tell me the date?
So it'll be on 16th of March before 12:30.
Okay, so we will have uh, I will email you the exact time. Can we have it 9:30?
Sure, sir. Just the way like class timings, or maybe
Yes, class
it's
time.
upon you. Like you can have it at 11 as well. Maybe we could have more time to.
And we can have 9:30 to 10:30, same thing. Is it all right to everyone?
Yes, sir. All right.
So 9:30 to 10:30 on 16th, we will have a minor one. Please do not make any unnecessary silly mistake and then run around me. It really becomes difficult to answer your queries on email, isn't it? Uh, Thankfully this time very few queries came, and please try to take your time, do your answering in a peaceful manner. Mostly the time is available with you, isn't it? The questions are not lengthy. Sufficient time is given. Sufficient time is given. Unless you make some silly mistake, you are not going to lose the marks. Okay. So we stop here and see you next week is the quiz. So Thursday will be the class next week.
No, sir. We have a major